Hello everyone, my name is Raviteja and today my topic is based on combining systems and databases, a search engine retrospective. To discuss about the data management challenges of a search engines. With over 3 billion documents, 10 TB of data and up to 150 million inquiries per day, with peaks of several thousand per second, search engines are the largest data management system in the world. There are more than 10 million possible words, and most searches yield thousands of results. Thus, the main issue is sorting through all of them. They hardly ever employ DBMS systems despite the scale and complexity of these systems. This is due to the fact that there is a semantic mismatch between the two. DBMS or slower, and they were not created to handle the particular problems that search engines face. Search engines adhere to the principles of top-down design and data independence and declarative query language, but not DBMS artifacts. High availability and freshness are two significant and difficult data management concerns, while freshness is a problem of keeping the index up to date with the data, which is primarily remote and rather challenging to access. Downtime directly contributes to lost income and customer attraction. Search engines which favor high availability above consistency do not require ACID transactions as their semantic model. The components of a search engine. The crawler, which examines websites in a similar manner to an end users and gathers them into a single file, is the first step in the search engine process. The crawler has to know which pages have already been crawled or now been done so, how frequently to crawl again, and something about mirrors, dynamic pages, and MIME types. After parsing and analyzing the text that have been gathered, the indexer creates a static database of normalized scores for each word in each document. The indexer's objective is to transfer workload from web servers to the indexer so that servers must perform less work for each query. In addition to this additional document analysis, the indexer additionally searches for spam, identifies the major language and region of the document, and keeps track of incoming and outgoing links. Tracking all of the anchor text for a document, which is the hyperlink text in all other documents that point to this article, is one of the more difficult cores for the indexer. At last, the server performs query processing, optimization, and execution before running queries against the database of indexed documents. Since the sole update action is the atomic replacement of a chunk, there are no logs, isolation problems, or requirements for concurrency control for queries. The access methods and physical operators. A sequential scan of a sorted inverted index, which is a sorted list of all texts that include a particular term, is the access mechanism utilized. Since expressions are a subclass of properties, any argument that anticipates a property list can be used with an expression list. To decrease query latency, intermediate data are cached, and the plan is not pipeline. The use of multi-way connects reduces the depth of a plan and requirement for estimating selectivity. The physical operators are OR, ORP, ANDP, and filter are the only ones available. Filter, which is essentially an AND of all its inputs and only uses the expressions to calculate the score, maps the majority of searches onto a 1D plan. We only need to estimate selectivity when a subgraph cannot be flattened to perform a multi-way join. The topic is the anatomy of a large-scale hypertextual web search engine. Google, a significant web search engine, and its design and execution are discussed in the study. To give people relevant search results, Google employs a variety of strategies, including crawling, indexing, and ranking. The system uses distributed processing and storage to achieve its goal of scalability, fault tolerance, and efficiency. The study focuses on the architecture and algorithm used for indexing and querying the web. This includes methods for data clustering and fragmentation as well as semantic multiprocessing for parallel processing. For load balancing and updating convenience, the document word and the property tables are horizontally split by doc ID. For effective querying, the term table is replicated on each node and the word IDs are assigned global values. The contents of the cache might differ between nodes, although this is typically not a concern because the clusters document are distributed erratically. The system has a master slave architecture, where the master node computes and optimizes the query plan before sending the request to the following nodes. Tricks for optimizing search engines. An important optimization that is underutilized in DBMS but is more appropriate for search engines is the compression of the inverted index. Simple and efficient compression algorithms make good use of all score bits and employ relative numbering for doc IDs. Decompression is easily accomplished on the fly by current processors, and compression enhances cache hit rate and effective disk bandwidth. The snapshot must correspond to the most recent version of the database, and preloading the cache at startup significantly reduces the mean time to repair for a node that goes down. By utilizing a master node, a patent optimization based on the conventional search algorithm is made possible. This approach was a conservative heuristic to trim the search space. The top k local research are computed by the masters, and the kth local result score serves as a quotient's lower bound on the top k results overall scores. This makes it possible to discard subqueries that fall short for this lower bound. Atomically installing new chunks and cache. A search engine's database is updated atomically when a new chunk is added, which includes adding one element per chunk to the version vector. Installing a new chunk is simple if caching is not present because the relevant file can simply be closed and reopened with the updated version. A management process can use Unix signals to remotely install chunks and start rollbacks to earlier versions of chunks without the need to stop the node. Smooth rolling upgrades and incremental updates can be made possible by automating the management process, which will lessen the effect of rebuilding the chassis. Update process and chunking in search engines. Crawling to find new contents is the first stage of an update. Indexing involves managing information and as well as analyzing and grading documents. A chunk is an average size collection of doc ID data. As the database gets bigger, the typical chunk size will increase until it reaches a certain size, at which point it may be divided into two or more chunks. Depending on the content, partition refresh speeds vary. Although adding new documents to current or brand new chunks is largely a different operation document discovered. Each chunk has a distinct version number that increases monotonically. This number is used for the data rollback, content debugging, and invalidating caches. Real-time deletion and updates in search engine. The process mentioned in the article does not entail record-by-record modifications. However, there are instances where altering a single document right once is required, such as when an illegal document needs to be removed when it is discovered. A mechanism for adding a row that indicates item deleted is introduced to the right-hand side of an anti-join to remove the document from a set in order to enable real-time deletion and updates. Every chunk receives the addition of a very small table that serves as a property table for the property has been deleted, and also a list of documents that have been removed. Is the fault tolerance for search engines. High availability is the main objective of fault tolerance for search engines. Since the indexing and the crawling process are independent of the server, high availability is not required. While it is not necessary to replicate the majority of documents for high availability, some partitions are replicated while others are not. Defects in non-replicated chunks and nodes or merely momentarily shrink the database size. By using pseudo-random doc IDs, we avoid losing all of the document from a single site and only lose a random fraction of the documents in a partition. Typical policies might copy well-known websites and premium content. To discuss about the types of faults. Disk faults. High availability is the main objective, which is attained of methodologies and optimizations. The crawling and indexing operation is not dependent on the server and just has to be idempotent. Only some partitions are duplicated while others are not, and the majority of documents are not worth replicating for high availability. The most frequent error is a disk failure, and the fresh copies of the affected chunks can be automatically switched in form of other blocks or disk after being loaded in the background. There is always plenty of spare space for staging because nodes are restricted by disk search rather than space. For replicating chunks, if the primary node falls during recovery, the other replica takes over. And for caching reasons, it is recommended to just have one replica process queries in the typical scenario. Next we come to follower faults. Follower and master node failures can be distinguished. An unsuccessful follower removes all of its pieces. If the master detects a failure, it will either continue without the data in the case of unreplicated system or get in touch with the secondary in the event of replicated system. Spreading the backup copies across the partition is a crucial optimization for distributing the directed load brought on by a problem. Although chain declustering is a possible method, there are many more appropriate places. The risk is that the secondary could fail earlier. Failed nodes are normally replaced later that day, but they can be replaced at any time. Replicated partitions should include more nodes than the degree of replication to enable fine-grained load balancing after a failure. The other one is master faults. Reissuing the query on a different master is a fundamental tactic for dealing with master failures. Initially, the master also served as a web server, making its failure apparent to outsiders. A layer 7 switch normally cannot reissue the pending queries at the moment of the failure, but it can hide failed nodes for switch searchers. The existing method isolates the web server from the master, allowing it to identify failures and resend unsuccessful queries to a different master. This smart client approach is superior for two specific reasons. First, the retry is transparent to the users, and second, it permits reissuing the query to a different data center, which promotes global load balancing and disaster recovery. And the next topic is overload management in internet scale services. Internet servers struggle with overload, and over provisioning is not a workable solution. Queue lengths are the basis for overload detection. When queues are excessively long, the system enters overload mode. There are two fundamental methods for graceful degradation: dynamic database reduction and cost-based query execution decline. Dynamically, reducing the size of the database increases the effective cache size for the remaining data and decreases the processing time for query. You can implement admission control by either outright rejecting expensive queries or by probabilistically rejecting requests. The log management system for a large-scale internet sites. Search engines provide vast amounts of log data for troubleshooting, paying advertising, and quality control. A distinct class of data-intensive systems called log management systems does not work well on top of current databases. DBMS traditionally do not handle large-scale real-time loading of data, and log records have a different update model from DBMS. Regular expressions, relative timestamps, and partial string matches are required by the log system. However, these features do not work well with the SQL. Database principles and the top-down approach still apply to log management system. The log system includes its own query language and optimizations, including compression, caching, and parallelization. Now, finally, we come to the conclusion that the paper makes the case that even when the artifacts do not match well, the concepts of database system should nevertheless be extended to other top-down data-intensive systems. It demonstrates how a top-down design with data independence and declarative languages can result in simpler, cleaner, and more reliable systems that are better optimized using examples from search engines, logging systems, distributed file system, workflow system, and bioinformatics. It is hoped that the systems and database sites can learn from one another's methods and produce the future ideas that are more adaptable and practical. Thank you.